we have 2 sections left. This one is sort of normal length, and then the last section is pretty long, meaning that there's just a lot of relationships to talk about in there. So that will probably take several days to finish. This one, I think, between today and then working on it tomorrow, I think hopefully you'll feel like it's going well and we can just wrap it up. So, inscribed angles. Do you guys remember what inscribed means? We've used that word a few times. Well, what does scribe mean to you? To write. And then in means inside. Okay? So an inscribed angle is inside, or an inscribed something is inside of something else. So in this case, inscribed angles are angles that are on the circle. So do you see any of those in these pictures? You should see one inscribed angle. It's an angle that's on the circle, meaning it's on the edge of the circle. Okay, so that angle is right here. Like that angle is an inscribed angle. And we can form these like that one with 2 chords or a diameter and a chord, or with a chord and a tangent line. So that would create an angle right there that we need to analyze. So not just parts that are hooked on only to the circle. And of course their relationships are going to be, hopefully it makes sense that they'll be related to arc measures and different things, okay? The good thing about these is the relationships are pretty easy. There's just several of them, so you have to remember them, but they're not like complicated formulas or anything. I have already started grading, and I do want to address this. So, what is that called? It's a chord. Is it a length or an angle? Huh? Length. So we deal with like centimeters, inches, Pythagorean theorem, those kind of things, right? Okay? And then if I talk about these 2 things, angle or length. Angle, so those are measured in degrees, right? Okay? This, degrees or length? Degrees, okay, we're talking about that angle. But if we start connecting, like maybe connect a tangent here and it's 90 degrees and we start drawing in this kite, that's not helpful. Okay, and we start talking about like this, is that length or angle? Length, okay. So far we've talked about both, right? And we are going to continue to talk about both, fortunately or not. You saw today we're talking about inscribed angles, so we're back to an angle topic. We just finished chords, which was mostly a length topic. Tangents was kind of both, but mostly length. And then the last topic is secants, which is going to have both angles and lengths. And so one of the things that gets hard about this is keeping that all straight. So we could, and I want you to kind of think about this as you write notes and study them, but one of the things that we could do is go categorize your notes better. Not better, but add categories in there, like this is angles, this is side lengths or something, just so you know which one you're solving for. Because I'm seeing some mistakes with that, and I mean, I think in general you know the difference between like an angle here and a length, right? But sometimes I think you might get the formulas mixed up, and that's where it might help to edit your notes a little. Anyway, grab your notes. And that's probably 4 boxes is close to enough. If we need one extra, we can do that. I've been trying to divide this up, with these section breaks like this. So if you have been doing that, yours are already kind of, I think, organized with categories, but if not, maybe add those in. So this is inscribed angles now. Can inscribed angles be part of a triangle? Do you suppose? Because we, even though we're talking about circles, we've seen lots of instances where we're dealing with triangles, though. And the answer is yes. Don't draw this, but I'll just show you what I mean. If I connect to a chord, if I connect these lines to make an inscribed angle on a chord, then yeah, that's a triangle. So, we'll do this simple. An inscribed angle is an angle with its vertex. What's a vertex of an angle? Okay, so the vertex is on the circle. And so just draw some version of that. This is angle BAC. And the vertex is right on the edge of the circle. What is forming it? What are those two lines called that are forming that angle? They're what? Those are chords, yeah. Okay? So let's put a little note about that. Formed by two chords. Okay. So that's the definition of an inscribed angle. Here's one relationship that we're going to talk about. Did you say that? Okay.
Measure?
That says measure. Like, how do we find it?
Oh.
Yeah. So the measure of an inscribed angle. We're going to write a formula, but I want to describe it so you know where it's coming from. Is half the intercepted arc. You guys remember what that word means, or that phrase, intercepted arc? It's the arc that's being cut off by these two chords, or formed, I should say. So let's do it this way. In your picture, for this one, do you see an arc that's being intercepted by those two chords? It's this arc right here. Arc BC. Okay, so the measure of angle A is 1/2 the measure of arc BC. Everybody see where that's coming from? What is the measure of arc BC congruent to? Okay, I don't want you to add this, but everybody put your pencil down. Just as a reminder, if I draw the center in here, arc BC is congruent to that central angle. Remember that? So you could also say that measure of angle A is half of the central angle of BC. Okay? So this is the one I want you to know. but it's not like that exists in a vacuum. Half the central angle of BC. Because those are congruent. So that's just a reminder. Like, we already wrote about the arc measure being congruent to the central angle, but there it is again. Okay? Let's draw a picture for the next one first, and I bet you'll be able to tell me what we're going to say about it. So draw, I need to turn that just a little bit. So we're going to intercept some arc with those two chords. If you have colors, it's kind of nice to have different colors for this. We're going to intercept the same arc with those two chords. So you see how they're overlapping the same arc right there. What do you think is true about those two inscribed angles? They're congruent, yeah, good. So we'll call this box congruent inscribed angles. Okay. So two inscribed angles that intercept the same arc are congruent. So what can we add to our picture now that we know that? Do you remember how to notate congruent angles? The little, well, it's the little arc mark, yeah. So mark those two angles as congruent. You guys remember me showing you the circle of doom? It relies a lot on inscribed angle stuff, or those kind of problems, I should say. Okay? Not just, but it does rely on that a lot. Okay, next, we are going to need a couple more boxes. Sorry about that. Are you sick of the word inscribed yet? I am. I was tired of writing it. So an inscribed angle of a diameter. Do you see how none of this is super, it's like half, right? Like the relationship is easy. It's just seeing it that sometimes gets hard. So what is, I bet you could tell me this before I even write it. What are we going to say about an inscribed angle of a diameter? In fact, why don't you, how do you show a diameter on a blank circle like this?
A line that goes to the central point.
Okay, so but that means we have to show the center, right? So put your center and draw your line through that. And then draw your inscribed angle. How many degrees should that angle be if it's inscribed to a diameter? Why?
It's like going to both ends of the diameter. So like
And how many degrees is a diameter? Like, how many degrees is the arc of a diameter? Yeah, okay? So we can just say is 90 degrees. And it's because it's intercepting a 180 degree arc. Okay, so I added a couple of those things to the picture. This is actually pretty useful. Have you ever tried to find the center of a circle? Like in real life, not on paper? Anybody ever had a reason? Like, what if you wanted to make... Let me think. Well, sometimes if you're building... I have built stuff at home where, like, if I want it round, obviously you can trace out that with a compass, right? But if you want to find the center of that circle to maybe drill a hole through, to hang it, or to have it as an axle, like for a place for an axle, how do you find the center of a circle? Huh? Who talked? Is that you? What'd you say? True, but it's hard. You gotta figure out where that center is, right? Like, you have a round water bottle. Where's the center of the bottle?
Well, it does show you where the center is.
It does?
Yeah.
Oh, that's cheating. Okay. Good job for them. Here's an example. Has anyone ever used a lathe in tech ed? So you take like some block of wood and you stick it on the lathe and it spins it, and you can use chisels to form it and shape it like into cylinder, like table legs, bats, like decorative things. Anybody ever done that? Okay. So, hi. Well, you guys need to get out more. What else? I'll try to think, but I remember when I didn't know this when I was trying to find that center of the circle. And what I ended up doing was frustrating, because I would like measure across different ways and hope that I found, a point where they all cross, but it's hard when you're doing it with real stuff, with a tape measure. It doesn't work out super well. But what's cool with this theorem, like I wish I had known this at the time, is I've talked to you about a carpenter square, which is like in the shape of an L. Maybe you've seen one before. It's bigger than this, but that's guaranteed at a 90-degree angle. So if you take that and you stick it on your edge of your circle, then you can draw that, and it's telling you where that center is. If you do it just a couple of times, then you hit that center point right on. And I wish I had known that, but now I do. Okay. So inscribed angle of a diameter. Guys, these are sometimes hard to see when you have lots of lines going on, and you're like, when you finally realize, you're like, dang it, that was so easy, it's 90, and you forget. Okay, so try to get that one locked in. All right, a couple more. Inscribed quadrilateral, what's that mean? Like, what is a quadrilateral? Give me a name of one. Square. It doesn't have to be a square, but that is one. Square, rhombus, trapezoid, rectangle, kite. Yeah, good. Alright, so you can pick one of those shapes to draw. Inscribed means it's drawn inside of the circle. And let's label each angle with a letter. This is kind of a cool thing. Remember all that work we did in the quadrilaterals unit, how much we had to like we had 6 properties of those, right? And we had to try to sift through and remember, oh, this one the angles do this and this one the angles do that. Here's what's cool about when you draw one in a circle. Here's what's true. You don't have to worry about if it's a trapezoid or a square or anything. Opposite angles are supplementary. You remember what that word means? Yeah. So, like in this picture, let's do a better one. Measure of angle A plus measure of angle C equals 180. And measure of angle B and measure of angle D. Doesn't matter what shape that quadrilateral is. It's the opposite angles will add to 180. So that's kind of neat. Oh. You happy about that? That's the way you're This does come up some if you happen to see the quadrilateral in figure. But also, this is how wood is cut typically, because what shape is a tree? It's round, right? So you don't need to draw this, but if I cut this log and we're looking at it end on, I want to cut out some block of wood out of it. Maybe we're using that theorem that we just wrote. All right, last one. I'm going to draw the picture. See if you can tell me what the pieces are called that I'm drawing. So, A, B, C. What is AB called? Good. And BC? Good. Awesome. So, this one, tangent chord angles. What do you think you might get this confused with if you're working, on a big picture, a whole bunch of problems or a whole bunch of angles? What could you possibly get that confused with? That you already know. Yeah, well, potentially. I'm thinking more maybe the tangent one. Go ahead.
Like tangent in diameter?
Yeah, tangent radius that's 90, right? Tangent radius or tangent part of the diameter. Okay. So this is not that. And it's not because it doesn't look 90. It's because it's not a radius, it's a chord. So be careful. So the measure, the angle formed by a tangent chord. Let me ask you before we write this, because we're running short on time. Is it okay if we just write the formula for B? Can you transfer that, or do you want a description first, like we did before? Just the formula? Are we good on that? Okay. And I'll write a little blurb, but you don't have to. All right, first of all, here, look here, because I want to show you how this can get a little bit confusing. Don't draw this on yours. But do you see, like, if this chord spanned over that direction, sometimes there's like a little gap there. And if we show the angle like that, do you see how we're dealing with the lines and the circle's just kind of in there? Okay? So this is not an angle between the chord and the circle or anything. It's between the two lines. Maybe that's not a big deal to you, like, you see it just fine. I just wanted to point it out because sometimes it looks kind of weird. Okay? So here's the relationship. Measure of angle B is 1/2 the measure of arc BC. So go ahead and highlight that arc. So it's half the intercepted arc. And I think this is probably what I was kind of trying to say is that arc sometimes looks kind of weird because your eyes want to follow the line, the tangent line out. We do probably need to say that AB is tangent and BC is a chord. Okay, notice we didn't write that it's 90. This is not. It's half of that intercepted arc. So let me flip this on you. How big is the arc compared to the angle? If the angle is half of the arc, how big is the arc compared to the angle? Here, don't draw this because it's just a quick example. If I tell you that this angle is, let's say, 20 degrees, how big is this arc? 40. You just double it, right? So double going out, half coming back in. That's the same for the one that we wrote about just plain inscribed angles as well. Okay, so let's look at some problems. That was too small. What is the measure of angle C? This angle right here. What's the measure of it? Raise your hand and you can tell me. Good, 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 good. What are you saying? 26, yeah, because this is a central angle, right? Central angle, which means we can copy that out here to the measure of arc AB, and then we can half that to get C. That's kind of the thought process. Good on that? Okay? We'll have to speed through some of these. All right, what is this kind of picture? Which theorem did we write about that looks like that? Yeah, good. So it says measure of angle or measure of arc DG. DG is 40. What was it? 45.8. I'll write it bigger. Okay. So what are those two angles? They're the same as each other, but what are they? Just ballpark it. Or just describe it. They're inscribed to the arc 45.6. So inscribed is what to that? Half of it, right? It's half.
22.3-ish.
Yeah, good. 22.8. In fact, let me go back and write that. Alright, see another couple. There's an inscribed quadrilateral. What was true about those? Like, it says BCD, so BCD, this angle right there. Oh, that's an arc, sorry. I read it wrong. Arc BCD is this whole giant arc right here, is 242. So what is angle? Here, look. I know you're packing, you shouldn't be. Do you see how this angle starts the arc clear back here at B and D? That's another thing that's sometimes hard to see about these is like, oh, I see this arc, but where's the angle? Oh, it's clear back here. How big is angle A? 121. Yep. So you're kind of seeing how this will be used? Now we have one with some more lines in it. Do you see in any inscribed angles? How many? 1, 2. Good. Okay. So you'll be working with this, like I said,